And so now I'm going to define a Hermitian operator, and our Hermitian operator is defined in this way. We have some Hermitian operator h hat is equal to h hat dagger. Right, so our Hermitian operator is its own Hermitian conjugate. And we can define this in another way using this up here, right? If we have some A inner product with h hat B, this is equal to h hat dagger, right? But h hat dagger is h hat, so h hat acting on A inner product with B, right? And this is going to be our more solid way of defining a Hermitian operator. Hermitian operator follows this. It can kind of hop the inner product. That is how we're going to define a Hermitian operator. And note, Hermitian operators are linear operators too. So Hermitian operators are linear operators, right? And so the other thing that I want to discuss here, and I'll prove this too, it turns out a linear combination, right? And this is, I'm going to have to preface this with C1, C2, C3, etc. are real. This only works if they're real, and hopefully you can see why. Right? If I take a linear combination of Hermitian operators, C1 times H1 hat plus C2 times H2 hat plus C3 times H3 hat plus dot dot dot, right? And if I take the Hermitian conjugate of this is equal to, well, think about the Hermitian conjugate, right? The Hermitian conjugate of a sum is a sum of the Hermitian conjugates, right? So this would be C1, right? This would be C1 H1 dagger plus C2 H2 dagger plus, plus dot dot dot, right? But then this dagger, right? The Hermitian conjugate of a product is a product of the Hermitian conjugates. And actually, I'll tell you that is not entirely true, but for right now and until section 5, it will work for us. So this, right, we can sort of distribute this Hermitian conjugate. Well, C1 dagger and C2 dagger and if they're real, this is just, they're scalars, right? And are real constants. Real constants, which are scalars, right? So they're real scalars. This means C1 dagger is C1 complex conjugate, which is just C1 because it's real, right? Times H1 dagger, which is H1, right? So because it's Hermitian, right? So if I just do this, we know that this is C1 H1 hat dagger, but that's right, plus C2 H2 hat plus C3 H3 hat plus dot dot dot, right? A real linear combination of Hermitian operators, Hermitian a real linear combination of Hermitian operators is linear, right? The other thing to note is multiplication by a scalar, right? So for example, 2 hat is Hermitian, and if we just think about it, right, 2 hat, right, which is defined as just multiplying by 2, well, what is, as long as it's real, right, this is another property that we'll have, I'll put it up here, multiplication by a real scalar is Hermitian, right? Because, 2 hat dagger is equal to 2 hat, right? Because it's real. Okay, so hopefully we have this down. These are just a few things, right? If we have, if we can combine different Hermitian operators in a superposition or in a linear combination, and they'll still be Hermitian, just like, and still then be linear as well. as we have talked about before. So hopefully this makes sense. If not, please rewatch this video. Make sure you understand these properties. I know this is a lot of information. This is so important for the rest of quantum mechanics. We will be dealing with operators literally until the end of this course. And operators are really one of the big foundations of quantum mechanics. We'll see when we get to the Schrodinger equation. It's all about operators. So hopefully you're getting this. I'm going to erase this, and we're going to get to our last part about Hermitian operators. And the last thing is I want to give three properties of Hermitian operators. Three properties of Hermitian operators that are that are incredibly important. And so the first thing I want to state here, and this is not a property, but this is sort of just a postulate. This is a postulate of quantum mechanics, and I'm going to put this up here. All physical observables are represented by a Hermitian operator. Right? All physical observables are represented by a Hermitian operator, right? Such that, Q hat, right? Q hat is going to be Hermitian. Q hat acting on phi sub Q is equal to Q phi sub Q, right? And these are actually this is actually another postulate of quantum mechanics. Different sources, generally people say there are 6 main postulates of quantum mechanics. This is one of them. We've already actually come up with a few of them about the inner products and the probabilities, right? Those are also some postulates of quantum mechanics that we are sort of gathering. And to put this in perspective, this all started with that Stern-Gerlach experiment, figuring out that everything had to be in a Hilbert space, and this has sort of all come from some basic ideas about Hilbert spaces. Right, so this is this is sort of my postulate, and I'm going to be showing you. I'm going to have 3 different properties of Hermitian operators, mathematical properties. 2 of them I will prove. The third one, there's a proof in the description. It requires a bit of linear algebra, so I'm going to ask you, if you don't understand linear algebra, to just sort of trust me on this, go with me, and in due time, if you take linear algebra, you'll be able to prove it. That's actually one of the things that we will not get to prove in section 5. It's just a little bit beyond the scope of this course. But if there are enough people that do want me to do a video on that, I can do an extra math video on that. But anyways, so number 1, I'm going to do this in a different color. I'm going to leave this up here. This is sort of our basic, what we're talking about right now. And we'll go through the different properties of Hermitian operators, and I will explain to you why this property, right? Why this property is necessary for a physical observable, right? And also note a property that I'm not mentioning here, and I'm sure there's a proof for it somewhere. I don't know if off the top of my head, I believe it's pretty elementary, but it's Hermitian operators are linear. Okay. So, but that's not one of the properties here. We're sort of just taking this, and you'll see in section 5 why that's so much of a given. So number 1 is the eigenvalues of a Hermitian operator. I'm going to just abbreviate Hermop. Hermitian operator are real. Right? And before we prove this, let's just think about why this is necessary for any physical observable, right? Any physical observable, right, if we're going to observe it, its eigenvalues, remember its eigenvalues are the actual values, right? If I have phi sub 1, right, this has an actual value of q equaling q1, right? the values that the observable can take on are the eigenvalues, right? This is the eigenvalue, this is the actual value of the observable, and it's got to be real. I can't be having an imaginary position or an imaginary momentum or an imaginary energy. Actually, we can talk. I think I will talk about imaginary energies. It's not really a real thing. No, I guess pun intended. But if you allow for imaginary energies, it can do a few cool things with modeling decay. Well, I think I'll get to that in section 4. But you know, in the quote unquote real world, we can't be having any imaginary energies, imaginary positions, imaginary momentums, right? That just doesn't make any sense. So the eigenvalues of any real physical observable operator, right, or any operator that represents a real physical observable, those eigenvalues have to be real because the value of the observable has to be real. And so when we do this proof, I'm going to assume that we have phi sub. I'm going to do this with phi sub 1, but it will work with phi sub 2, phi sub 3. You'll see it doesn't matter what label I put on this, right? Actually, I can do this. This one I can do in general with phi sub q, right? We're going to assume that this is not equal to 0. Otherwise, the function itself will be pretty trivial, right? If we have a vector here that's 0, right, then it wouldn't really make any physical sense, anyways. Right. So let's look at this. If I have phi sub q inner product with q hat times phi sub q, or q hat acting on phi sub q, right? Well, this is q hat. Q hat acting on phi sub q is going to give me q times phi sub q, right? So this is phi sub q inner product with q times phi sub q, right? Which is, well, remember, we can take this constant outside of the inner product. So this would be q times phi sub q inner product with phi sub q, right? Well, let's look at the same thing here. This is also equal to, well, if q hat is Hermitian, right? Assuming q hat is Hermitian, right? Because we're proving this property for Hermitian operators, so q hat is Hermitian. Q hat times phi sub q. Q hat, right? This is equal because it can hop the inner product. That's our definition of a Hermitian operator. Q hat acting on phi sub q inner product with phi sub q. Right. Well, this is right q phi sub q inner product with phi sub q. And we can take this q outside of the inner product, but remember, when it's in this bra vector, we have to take its complex conjugate. That was covered a few videos ago. So this would be q star times phi sub q inner product with phi sub q, right? So now we know that these two things here, right? These two things are equal to each other. And as long as phi sub q is not equal to 0, right? This inner product is not going to be equal to 0 because it's the magnitude squared of phi sub q, right? So it could not, right? So unless phi sub q is 0, which we're assuming it is, and otherwise this would be trivial, right? So if phi sub q is not equal to 0, that would mean that q is equal to q star, right? Which means q is real, right? So cool. We proved this property, and thankfully we did, because otherwise our physical observable would not make too much sense. We have the eigenvectors of the eigenvectors of Hermitian operators with different eigenvalues are orthogonal. Right? And this is also important because if we think about our probability postulate, right? Well, what is this inner product if I have phi1, phi2, right? This is saying, if I have a particle in the state phi2, right, which means it has a value of the observable being q2, right? Assuming that q1 is not equal to q2, right? This has got to be equal to 0, because otherwise I'm basically saying I'm asking you, you know, what is this is, the square root, right? Norm squared is the probability, right? That if I'm in the state phi2, I have a value of q being equal to q1, right? But if I'm in the state phi2, that means q is equal to q2, right? And so therefore the probability of having q1 in the state with q2 will obviously be 0, right? Unless q1 equals q2, right? So this has to be true for a physical observable to work with our probability postulate, right? So we're going to again assume q1 is, right, not equal to q2. Right, and you can do this q2 and q3. Any q, I might even call this qm. Yeah, why don't we do that? We'll say qm is not equal to qn. Right? And so now let's look at this. Is actually pretty similar to what we did in the first proof. Let's take, right, phi m inner product with phi n with q hat acting on phi n, right? And this is equal to phi m inner product with qn times phi n, right? Which is, right, we can take this constant out. This is qn times the inner product of phi m and phi n. Right? Well, now let's look at this. This is also equal to, well, this is a Hermitian operator, so it can sort of hop the inner product. Q hat acting on phi m inner product with phi n, right? Which is qm phi m inner product with phi n, which is, we can take this out, but it's got to be complex conjugated. So qm inner product phi m phi n, right? But remember, because this is a Hermitian operator, qm star is equal to qm, right? So this is qm, because qm is real, phi m phi n, right? And assuming, right, qn and qm are different, the only way that these two can be equal is if phi m phi n equals 0. Right? These two have to be equal. The only way that's possible, unless qn and qm are equal, that would mean phi m and phi n have to both be 0. Right? Phi m phi n must be equal to 0, right? Assuming m and n are not the same, right? We assumed before in the other video, right? qm was not equal to qn. These are each distinct states with distinct values of the observable, right? So if they don't have the same value of the observable, they're orthogonal, which makes perfect sense according to our idea of a physical observable. So that works out perfectly. Again, if you're not following the proofs, they're pretty basic. You may want to review them a few times because it's a good math skill to be able to have to look at these proofs. They're basic enough that it will be good for your mathematical thinking to grasp these proofs. But if you don't, it's not the end of the world as long as you kind of buy into the result. Now this third one I'm going to state without proof, again because you need a bit more linear algebra than we're going to have in this course in order to get this proof. But in the description, I do have linked a pretty beautiful proof for this, and I'll describe it a little bit in the description because it uses slightly different notation, but that's all right. It's beautifully presented, right? So our third property is the the eigenvectors the eigenvectors of a Hermitian operator um, form a complete basis, right? And so here, the only thing I'm going to do is just explain why this is necessary for an observable quantity, right? And so this is saying that all the eigenvectors of a Hermitian operator form a complete basis, right? If it is a complete basis, right? And then this is sort of a definition. If the phi sub j basis is complete, any psi can be expressed as, right, the sum over all possible values of j, c sub j, phi sub j, right? This is what it means for the basis to be complete, right? And if we have, say, the energy operator, right? For example, the energy operator, right? All of its eigenstates, right? The state corresponding to E1, to E2, to E3, to E4, to E5, on and on, right? That is the set of eigenvectors of the energy operator, right? So the set of eigenvectors of the energy operator will contain every single state with every possible energy, right? Well, any state psi should be, right, in terms of energy, we should be able to express it as a superposition of all the states with all the possible energies, right? There can't be, some missing part of psi that can't be described by any state with any possible energy, right? That wouldn't make sense, right? Psi's got to be fully expressed by a superposition of these observables, right? It wouldn't make sense to, if for example, for color, if white and black were the only possible colors, psi has to be fully expressed as, you have some coefficient of white times the white unit vector plus some coefficient of black is the black unit vector, right? Psi has to be fully expressed in this basis, right? There can't be some other part of psi that is not accounted by the possibility of being white and black, because it can only be white or black, right? So this is, right, if any psi can be expressed like this, it is a complete basis, right? And Hermitian operators, right, represent the eigenvectors of a Hermitian operator represent all the possible states of a definite value of the observable, right? So all the possible states of the definite with a definite value of q. And you've got to be able to express psi in terms of all the possible states with a definite value of q, right? Otherwise, there's that missing piece, and it just doesn't make sense whatsoever. You can't have some probability that it doesn't have a value of q. It's a physical observable. It's got to have some value, even if that value is 0. Right, so hopefully that makes sense. And if it doesn't, just think about it a little bit more. Why this is so crucial, right? And that explains sort of why this third thing, right? It's a property of Hermitian operators. You can prove that with linear algebra. And now, and now we see, right, based on these three things that we would say any physical observable has to have, right? It's you got to have a complete basis of that observable, right? I'll state that again. Any possible state, we'll go back to energy, has got to be some superposition of having energy E1 and energy E2 and energy E3 and energy E4 and on, all possible energies. The state's got to be fully described as that a superposition of every possible value of the observable, right? That just makes sense. You've got to have that, or else, the state is not, there's like, some probability it doesn't have that observable, or, right, something weird like that. So with those three properties, right? We can state this. All physical observables are represented by a Hermitian operator with this eigenvalue equation, and that's operators, and we're going to be dealing with them for the rest of this course. So I'll see you in the next video.